In this lesson, we are going to talk about a very basic device, and yet one that is fundamental to every electronic device that we are using now, such as your mobile phone, your computer, your headset, energy-saving lights, and your TV, to name a few. Practically all electronic devices have this. It's called a transistor. We'll discuss the most basic type of transistor, how it works, and its characteristics. A transistor is a semiconductor device with at least 3 terminals. The idea of having 3 terminals is that the first 2 terminals allow the flow of current through it, while the third controls the amount of current passing through the 2 terminals. The applications include amplification of a signal or switching, which is the basic requirement for any digital device. Thus, all digital devices have transistors present inside it. In fact, a single computer processor currently contains more than 290 million transistors, specifically for Intel's 65nm process technology. In the very first transistor, 2 closely spaced gold point contacts are held in place by a plastic wedge on a sliver of germanium. This germanium was n-doped, meaning that they are bombarded with these group 5 elements in order to replace the germanium atoms inside the material. Current flows through the collector lead to the base lead. They were able to control the amount of current by applying a small amount of current through the emitter lead. With the right amount of emitter current, they were able to change the N-type to a P-type locally, that is in the region near the gold foils. A small change in current through the emitter caused a large change in the collector current. Thus, they had created a current amplifier. Who were the inventors of this transistor? The inventors were William Bradford Shockley, John Bardeen, and Walter House Brattain. They were awarded the Nobel Prize in Physics in 1956 for their researches on semiconductors and their discovery of the transistor effect. Their discovery and invention led to the advances in the digital age, beginning with the computer, along with modern-day electronics. In 1972, one of them, John Bardeen, was awarded another Nobel Prize in Physics for the fundamental theory of conventional superconductivity known as the BCS theory, together with Leon Cooper and John Robert Schrieffer. The most basic transistor is called the bipolar junction transistor, or the BJT. The BJT is constructed with 3 doped semiconductors separated by 2 PN junctions. Thus, a BJT can either be an NPN transistor or a PNP transistor, 3 doped semiconductors with 2 PN junctions. The base region is lightly doped. The collector region is moderately doped, while the emitter region is heavily doped. For an NPN transistor, the collector terminal is connected to a moderately doped N-type region, while the emitter is connected to the heavily doped N-type region. The base terminal is connected to the middle P-type region. The PN junction between the collector and the base is called the base-collector junction. The PN junction between the emitter and the base is called the base-emitter junction. In a PNP transistor, the collector terminal is connected to the moderately doped P-type region, while the emitter is connected to the heavily doped P-type region. The base terminal is connected to the middle N-type region. The leads are labeled E, B, and C for emitter, base, and collector respectively. The term bipolar refers to the use of both holes and electrons as current carriers in the transistor structure. The inset shows the schematic symbols for the NPN and the PNP bipolar junction transistors. In reality, the structure of a transistor is a multilayer system, or in technical terms, epitaxial planar structure, as shown in Figure 4-1a. The substrate is made from silicon. Certain parts of silicon are covered with a mask. The exposed parts are bombarded moderately in group 3 or 5 elements, depending on whether the transistor is a p-type or an n-type respectively to create the collector region. This is the process called doping. Once finished, some parts of the doped material is then etched and then another mask is placed. The exposed part is then bombarded lightly with a group 5 or 3 element to create the base region. Once more, some parts of the doped material are then etched and another mask is placed. And the exposed parts are then bombarded heavily with a group 3 or 5 elements to create the emitter region. Once done, the last mask is placed in order to deposit the metal material that will connect to the lead wires. I included a video describing this process in our VLE. Take a look at it after this video. In our discussions, we are going to talk mostly about the NPN junctions. The PNP junction works in precisely the same way except the direction of currents are reversed, which means that the biasing is also reversed, and that the majority carriers are holes. For the NPN junction, the collector terminal is connected to the positive terminal of a voltage source. The base terminal is connected to the positive terminal of a second voltage source, while the emitter is connected to the common ground or the negative terminal of the two voltage sources. For the PNP junction, the voltage sources are inverted. The positive terminal of the first voltage source is connected to the emitter terminal. The positive terminal of the second voltage source is also connected to the emitter terminal. The negative terminal of the first voltage source is connected to the collector terminal, while the negative terminal of the second voltage source is connected to the base terminal. As we've previously mentioned, the base terminal is lightly doped. The collector terminal is moderately doped, while the emitter junction is heavily doped. Because of this, the PN junction between the collector and the base has a larger depletion region compared to the depletion region in the PN junction between the emitter and the base. Remember that the PN junction is formed because electrons and holes in the P and N-type regions attract but cannot combine. Because the relative amount of the dopants is smaller between the collector and the base compared to the emitter and the base, the PN junction is therefore thicker. Because the emitter terminal is heavily doped, when a voltage source is applied as shown, the electrons in the emitter can easily diffuse through the thin barrier between the base-emitter junction. A few of these electrons actually recombine with the holes in the base terminal. However, not all electrons can recombine because the base terminal is lightly doped and there aren't enough holes to recombine with. Thus, they diffuse through the thicker barrier or the base collector junction. What happens to the electrons that recombine with the holes? After recombination, they lose energy and drop down to the valence band. They then become valence electrons and are responsible for the current flowing through the base terminal, since they are attracted to the positive terminal of the base supply voltage. But what about the electrons in the collector terminal? They are attracted to the positive terminal of the collector supply voltage, move out of the collector N-type region towards the lead wires passing through the voltage source, and then goes back to the emitter N-type region. Since the emitter is the source of the current that goes through to the base and the collector current, then we can write the following equation as shown. I sub E is equal to I sub E plus I sub B. The emitter current is just the sum of the collector and base currents. Remember that the base current is very small compared to the emitter current or collector current. In a PNP transistor, these situations are reversed. However, this equation or relationship is true regardless of whether it's an NPN or a PNP transistor. The figure shows the basic schematic diagram for an NPN and a PNP transistor. The resistor connected to the base terminal is called the base resistor, R sub B. The resistor connected to the collector terminal is called the collector resistor, R sub C. The voltage source connected to the collector and the emitter terminal is called VCC voltage, with the positive terminal connected to the collector. The voltage source connected to the base terminal and the emitter terminal is called the VBB voltage, with the positive terminal connected to the base. VBB forward biases the base emitter junction, while VCC reverse biases the base collector junction. The voltage across the base with respect to the emitter is the base emitter voltage VBE. The voltage across the collector with respect to the base is the collector base voltage VCB. The voltage across the collector with respect to the emitter is the collector emitter voltage VCE. Since the VBB forward biases the base emitter junction, we can consider the voltage across the base and the emitter VBE to be approximately equal to the barrier voltage of 0.7 volts. We define the DC current gain of a transistor as the ratio of the DC collector current IC to the base current IB and is designated as DC beta. The typical values of DC beta range from 20 to 200 or even higher. On transistor datasheets, DC beta is more known as the parameter HFE. The ratio of the collector current IC to the emitter current IE is the DC alpha with typical values ranging from 0.95 to 0.99 and is always less than 1. This should be fairly straightforward since the emitter terminal is the most heavily doped terminal compared to the base and collector terminals. The voltage across V sub RB is computed from the difference between the base voltage and the base emitter voltage as shown. VRB is also equal to IB times RB from Ohm's law. The voltage at the collector with respect to the ground emitter is the difference between the collector voltage and the voltage across the collector resistor V sub RC. Finally, the collector voltage with respect to the base, VCB, is just equal to the difference between VCE and VBE. This is nothing but the reverse bias voltage between the emitter and the base. Let's consider this example from our reference material. Determine the base current, the collector current, the emitter current, the base emitter voltage, the collector emitter voltage, and the collector base voltage in the circuit of figure 4-9. The transistor has a DC beta of 150. We know that VBE is equal to 0.7 volts. We can then solve for IB, IC, and IE, and from there solve VCE and VCB. IB can be solved by taking the difference between VBB and the base voltage with respect to the ground. The base voltage with respect to the ground is just VBE, since the emitter is connected to the ground. Thus, IB is equal to VBB minus VBE divided by RB, or 5 volts minus 0.7 volts divided by 10 kilo ohms, which is equal to 430 microamperes. Now, since we already know IB, we can compute IC knowing BDC, or DC beta. IC is equal to DC beta times IB. DC beta is 150 and IB is equal to 430 microamperes. So IC is equal to 64.5 milliamperes. Now, since we know IB and IC, we can therefore compute for the emitter current, which is the sum of just the collector and base currents. If we sum 64.5 milliamperes and 430 microamperes, we get 64.9 milliamperes. So now that we know these three currents, we can now solve for the collector emitter voltage and the collector base voltage. The collector emitter voltage is just equal to VCC minus the voltage at this point, which is ICRC, okay, which is the voltage across this resistor. So VCC minus ICRC is equal to BCE, or 10 volts, minus IC, which is 64.5 milliamperes, times RC, which is 100 ohms, is equal to 3.55 volts. So the potential from this point to this point is 3.55 volts. VCB is potential between this point and this point is nothing but the potential between this point and this point, and the potential minus the potential between this point and this point. So it's just 3.55 volts minus 0.7 volts equals 2.85 volts. Using the basic transistor circuit for an NPN BJT transistor we've seen earlier, we can generate a set of what are called collector characteristics curves that show how the collector current varies with collector to emitter voltage for various values of the base voltage. We begin with the base voltage VBB equals 0 and VCC equals 0. We keep VBB equals 0 and begin to increase VCE. As VCC increases, the current IC increases and therefore the voltage VRC. Since there is no base current, all current is used up, so VRC is ideally equal to VCC. There is still a small amount of current through VCE because of the resistance through the tunnel barriers, which thins out as VCC is increased. This is why IC has a slowly increasing trend with VCE. At a specific VCE, the potential barrier breakdown and the IC increases significantly. This point is called the breakdown voltage, and is in principle the same as the breakdown voltage for diodes. The shaded region below the IC versus VCE curve for IB equals 0 is called the cutoff state of the transistor and is the non-conducting state of the transistor. It's also called the leakage current. The leakage current is mainly due to thermally produced carriers. It is highly exaggerated in the figure. When VBB is not equal to 0, IB is also not equal to 0. VBE is forward bias, as we very well know, and has a value of 0.7 volts. If VCC equals 0, then VBC is also forward bias. As VCC slowly increased up to the barrier voltage 0.7 volts, IC quickly increases because VCE remains less than 0.7 volts. When both junctions are forward biased, such as in this case, the transistor is in the saturated region of its operation. Saturation is the state in which the collector current has reached a maximum and is independent of the base current. As VCC is increased and VCE exceeds 0.7 volts, the BC junction becomes reversed bias. Most of the voltage is then dropped across VCE because the barrier across BC begins to thicken. Thus, the current IC hardly changes or increases slightly, and the expression relating the base current to the collector current via DC beta is no longer valid. It increases slightly because the barrier across BC thickens, which means that the base current increases since more electrons combine with more holes and diffuse less through the base collector barrier. This region in the IC versus VCE curve is called the active or linear region, and when VCE reaches a high voltage, the base collector junction breaks down and the collector current increases rapidly. The cutoff and saturation can easily be illustrated in the IC versus VCE curve or the collector characteristics curve through the use of the load lines. The load line is determined by connecting a line from the cutoff voltage to the saturation current. The cutoff voltage is easily determined since this is the voltage corresponding to when IC equals 0. If IC equals 0, then VCE is just equal to VCC. The saturation current is basically when VCE equals the saturation voltage across the collector and the emitter. We'll talk more about the load line in succeeding lessons when we apply them to other types of transistors and transistor biasing circuits, and when an AC bias is included. Let's consider this example. Determine whether or not the transistor in figure 4-16 is in saturation. Assume VCE saturation equals 0.2 volts. From this circuit, we can solve the IC saturation to be equal to VCC minus VCE sat over R sub C. VCC is 10 volts. VCE saturation is given as 0.2 volts. and RC is equal to 1.0 kiloohms. Thus, IC SAT is equal to 9.8 milliamperes. Now let's solve for IB. IB is the current through RB, and it can be solved by taking the difference between VBB and the current or the voltage at this point, which is just 0.7 volts. So 3 volts minus 0.7 volts divided by RB, which is 10 kiloohms, gives us 0.23 milliamperes. Knowing IB, we can then solve for IC using beta DC of 50. So 50 times 0.23 milliamperes is equal to 11.5 milliamperes for this, the collector current. Now, the saturation current is 9.8 milliamperes, which means that the collector current cannot exceed 9.8 milliamperes. Since we computed for IC to be equal to 11.5 milliamperes, we know that the transistor is now in saturation. Let's solve this next exercise. Determine whether or not the transistor in figure 4-16 is saturated for the following new values. DC beta equals 125, VBB equals 1.5 volts, RB equals 6.8 kiloohms, RC equals 180 ohms, and VCC equals 12 volts. We can solve for the IC saturation to be equal to VCC minus VCE saturation divided by RC. Since VCE saturation is not given, we can use saturation voltage equal to 0.7 volts. So 12 volts minus 0.7 volts divided by 180 ohms is 62.8 milliamperes. Now let's solve for IB. IB is just VBB minus VBE divided by RB. Since VBB is equal to 1.5 volts, then we know when we get, and RB is equal to 6.8 kiloohms, then we get IB to be equal to 0.12 milliamperes. Multiplying IB by DC beta of 125, we get IC equals 4.7 milliamperes. Now 14.7 milliamperes is a small value compared to 68 milliamperes. Therefore, this circuit is not in saturation and is in the active region. I hope you've learned what a transistor is, how it works, how to set up a basic transistor circuit, and how to characterize its properties. In the next video, we'll learn more about its specific applications as an amplifier and as a switch, and discuss some other biasing techniques. We'll also briefly discuss one interesting variation of a transistor, which is a phototransistor, and its application in solar energy harvesting.